Yes, well, thank you very much for the opportunity to speak at this meeting. I was asked to kind of perhaps give a little overview of asymptotic safety, and the way I want to structure it today is essentially in three parts. We'll give you a glimpse of the type of exact results we know in quantum field theory about what is called asymptotic safety. I will then try to show you how some of these ideas are explored in the context of gravity and what type of results people have come up with up to now. And I would then like to show you some applications of these results to the context of black hole physics and potentially black hole thermodynamics and so on. Okay, now some of the papers underneath it, I gave you some of the references here. Okay, I mean throughout the talk I will also give you some more indications on what's more literature in case you're interested to look some of these things up yourself. Okay, so now asymptotic. Hoppla, that's the page missing. No. Okay, so in a way, now we are all aware of this totally successful marriage between these two fundamental parameters. We call this marriage quantum field theory. It seems to be working extraordinarily well. My experimental friends tell me probably even too well because they don't manage to find deviations from standard model physics at the LHC these days, which is causing a tiny bit of frustration to them. But nevertheless, it seems to be an extraordinarily successful and useful framework to operate with. Now, one of the perhaps more interesting open questions is how the marriage between general relativity and quantum mechanics could actually look like. Now, of course, there are proposals on the market, some of which have quite a few strings attached, weakly coupled ones. But the big question, of course, from our angle would be, is there a way to formulate a consistent, conventional local quantum field theory which does involve, in 4 dimensions, a propagating, say, spin 2 degree of freedom, such as the graviton? Or, the other way around, is there any fundamental obstacle such that there is no conceivable way in which a setting of local quantum field theory could make sense for this? We all know very well that the answer within perturbation theory to this question is to the negative. Okay? Now, asymptotic safety is, say, the attempt to perhaps answer the question whether non-perturbatively, in some non-trivial dynamical sense, the answer could perhaps be yes. So just because it doesn't work perturbatively, this does not necessarily exclude that something non-perturbatively in those degrees of freedom can make sense at the end of the day. Okay. So even looking at this from a different point of view, I mean, in a sense, we know that in the conventional setting, quantizing degrees of freedom, spin 0, 1, half, and 1, works totally nicely. Okay, but the question here would be, is there an obstacle to quantizing spin 2? Good. Okay, so let me get started then. I would like to start with a brief overview of exact results about the phenomenon of asymptotic safety. And the way you might want to look at it is in the spirit of, say, some toy model quantum field theory, which has a relevant coupling constant, let me call it alpha. Let's assume that we know some RG equations for this coupling constant, where T is the logarithm of some RG scale mu. And let's try to write down the simplest form of such an RG equation. Okay? So a quantity which I'd like to write down as a toy model quantum field theory is this. It has 2 terms. One term which is linear in our hypothetical coupling alpha, and another term which is quadratic in this hypothetical coupling. So of course, you might think of this being a toy model for gravity, in fact, because imagine that you define the coupling as being G Newton, so energy-dependent coupling multiplied by the Rg scale to the power d minus 2 to make the coupling alpha dimensionless. Okay, and in fact, if you now imagine that you were to be working in d equal 2 plus epsilon dimensions, yes, then the quantity A, which is nothing else but the canonical mass dimension of the graviton, would be epsilon. Okay? Now, the second term here in this equation would be nothing else but the one-loop coefficient of the corresponding beta function. In this particular example, it would be the beta function in 2 plus epsilon dimension. And if we were to be imagining epsilon to be a small parameter, then, of course, it's the coefficient in 2 dimensions. Now, technically speaking, or formally speaking, in 2 dimensions, gravity would be a theory which formally would seem perturbatively renormalizable, because in 2 dimensions, the canonical mass dimension vanishes. And so, on paper, the theory would look not so dissimilar from well-known 4-dimensional quantum field theories which have dimensionless coupling constants such as QCD. Okay. Be it as it may, let's come back to the idea that gravity, of which we know that above 2 dimensions, gravity is getting a positive canonical mass dimension. And so according to our conventional understanding of quantum field theory, this theory is going to be perturbatively not renormalizable, no matter how small epsilon. Okay? So this is why this equation or this setting would be a useful toy model to consider the concept of asymptotic safety. Now, asymptotic safety then is requiring that a theory, could still make sense fundamentally if dynamically it is going to develop an interacting high-energy fixed point. Now, how could this interacting high-energy fixed point look like? Now, on the level of this simple beta function, we can immediately write down the condition for a non-trivial fixed point. So, what are the fixed points of this equation? There's the obvious one, which is coupling equals 0. Then each term individually vanishes. Fine. Of course, that's the free theory fixed point, which always exists. But a non-trivial fixed point can exist if these two terms then cancel out. So a non-trivial fixed point would then, in this convention, be located at A over B, where, as we said, A, in our take on this model, is a very tiny number, epsilon, and B is a number of order 1. So consequently, this fixed point coordinate would be, by its very construction, much, much smaller as 1, as small as we would like it to be. So this is how, in this model consideration, we can make sure that this perturbative reasoning is applicable. Good. So, of course, now for gravity, these studies have been put forward by Christensen and Duff, Gustman, Kalosh, and Truffin back in the late 70s. Okay? So they've computed this coefficient B. They figured out that the coefficient B indeed comes out positive to make sure that the fixed point is physical. It's in the domain where gravity is an attractive interaction. Okay? Of course, Meinberg also looked into this, and he then invented the name of asymptotic safety for this scenario in gravity, and since then it has become a marker for this type of, for this line of reasoning. Okay. Now, of course, this idea works very well because we make space-time continuous artificially by introducing a small parameter epsilon. Now, the big question, of course, would be, is this of any use for our understanding of gravity in 4 dimensions? Okay. Now, epsilon equal 2 is very big. Okay, and so in order to make it to 4 dimensions, you even have to cross 3, with 3 in its own right is quite special in a number of ways. So you might ask yourself whether this is really giving us good guidance for the physics in 4 dimensions. Okay. Be it as it may, I mean,
It's even worse than that. 4 dimensions, you have relevant operators, marginal operators that appear.
Yes.
You can't stick with this one.
You're absolutely right, of course. Yes, it's even worse here if you look more neatly into it, of course, because if you do the counting properly, to equal 2 dimensions is a setup where symmetry overweighs dynamics, and so the effective degrees of freedom in 2 dimensions, of course, is -2. So you may wonder what kind of funny theory this really is. Okay, be it as it may, this was a starting point for considering asymptotic safety in some form. Now, of course, you can now generalize this game, and you may ask, okay, do we have any examples for other degrees of freedom, such as fermions, to display interacting high-energy fixed point, as opposed to free ones, such as asymptotic freedom, the way we know it from the standard model? Now, for fermions, actually, you can do a very similar game. Yes, think of some 4-fermion theory, like, say, a Gros-Neveu type model. In this case, this coupling alpha here would be the Gros-Neveu coupling times mu to the power 2 minus d. Okay? And qualitatively, exactly the same beta function arises with structurally the same UV fixed point. Now, here's one interesting thing. This was first noticed by Gawecki and Kopien in 1985. Now, what these gentlemen managed to do is they picked up on an idea put forward by one of you in 1984 to prove the perturbative renormalizability of phi to the 4. Now, what they did is they used the exact same language and technology to prove the non-perturbative renormalizability of Gros-Neveu-like theories. Okay? So why is this interesting? It is interesting because it tells us something about the use of advanced Wilsonian renormalization group techniques in order to address physics questions in theories which may or may not develop interacting UV fixed points. Okay? So there exists an exact hard proof of existence for this phenomenon and these type of theories. Good.
Their exact rigorous proof is for what dimension? 3?
Well, this proof is technically in 2 plus epsilon. There is a 3-dimensional proof where the idea of the proof works in a slightly different way, where A, of course, is then 1. Okay, but if you do a large n, then B is of order n, and of course you know. Yes, but so this proof has been done later by De Callan and co-workers in 1991. So that proof exists as well in D equals 3. Good. Okay, just allow me. Yes.
I don't have any proof for it's actually more complicated for D equals 4.
It is more complicated for D equals 4. I'm not aware of a proof in D equals 4 indeed.
Yes. It does require under.
Yes. Now, let's walk our way through the degrees of freedom we know. Gluons. So for gluons, we know that in 4 plus epsilon dimensions, the theory can develop an interacting UV fixed point. Then alpha is nothing else but the Young-Mills coupling multiplied by mu to the power 4 minus d. So this, to my understanding, has first been observed by Peskin in 80. Later on, Tim Morris in 04, by the time that we knew the beta function coefficients up to 4 loop, managed to give an estimate for the resummed series, suggesting that this type of fixed point may even exist in 5 dimensions where epsilon is equal to 1. Good. Last but not least, scalars. What do we know about scalars? Now, 2 things. Scalars can have a linearly realized or a non-linearly realized internal symmetry. If it's non-linearly realized, then the theory is perturbatively non-renormalizable above 2 dimensions. And then once again, the coupling alpha is then that non-linear, the coupling of the non-linear sigma model, okay, dressed with the corresponding power of the RG scale. Now, if you think about linearly realized scalars, there it doesn't work. Okay? There it doesn't work, and you very well know that, because this is the reason of existence of the infrared fixed point, the Wilson-Fisher infrared fixed point in 3 dimensions. The reason being that B comes out with the opposite sign in that case. Okay? So for linearly realized theories, therefore, if we introduce an alpha, say with a conventional quartic coupling lambda times mu to the d minus 4, yes, then the corresponding fixed point is an infrared fixed point, the Wilson-Fisher fixed point. Good. So that's all we know. That's all we know in a hard way. Okay? Hard way meaning we know exactly how perturbation theory works. We have a trick, 2 tricks, to generate a small parameter. Trick number 1, introduce epsilon, so make dimension continuous. Trick number 2, make a large n, but then we can push it up to d equals 3, but we cannot deal with d equals 4 for now. Good.
Aren't there supposed to be like Chern-Simons matter examples in 3 dimensions with direct fermions, where you?
There might be some. I'm not aware of them, but if you
she would know probably, right?
Yeah.
Yes, right. Yes.
There are some models which have an exact controlled UV fixed point.
Yes, because they're exactly completely very Lagrangian.
Yeah. Yeah.
You mean
Okay.
like this,
So I will add them to my list. Thank you very much for that. So that's in 3 dimensions then?
Yes.
Yes.
But all you're saying, all you're saying here is some CFT in UV that is a relevant deformation that flows to some free theory. You know, I would know tons of examples beyond this list.
Yeah.
What's the reason for restricting this list then?
Can you say it again, please?
I mean, yeah, by now we know tons of examples of conformal field theories that may be strongly coupled, but still have a lot of control with a relevant deformation that flows to some theory that may be some free theory of massless fields in the IR. I mean, there are tons of examples beyond this list.
Yes, I'm interested in examples where I have exact control in conventional quantum field theory, like within perturbation theory.
I mean, we do have control over many of these theories, maybe not with the standard perturbative technique, but...
Like this one is just basically large n, right? I mean,
Sorry?
Well, like these Chern-Simons matter ones, I can get large n.
You don't even need large n. Those are under control, even perturbative in the Chern-Simons couple.
Yeah.
But I'm not even talking about that.
Yeah, just more general.
Good. So, what I want to make here is that this is what we know and can control in perturbation theory, but there is an obvious elephant in the room.
So sorry, can
yes.
I just add? I mean, there are also, of course, another class of well-understood examples, which are integral models in 1+1 dimension. We have non-trivial Schrödinger deriving CFT in the UV, and the flow to some theory in the IR maybe can be massive, maybe massless.
I think the point here is different. He's listening. The point here is he's trying to construct, starting with perturbative general relativity, a UV fixed point. So if you can guess it, that would be great. He's trying to use perturbation theory to probe that possibility. Correct?
Thank you very much. Yes. Okay. Now the point I'd like to do next is there's a problem with this list. Now, the problem with this list is that nowhere on this list d equal exactly to 4 appears. Okay. And so in a way we want to use these set of ideas to attack gravity in 4D, but we are not even aware of a simple any example where this type of mechanism seems to be operating in exactly 4 dimensions. Now, I happen to have an example where this actually works in d equal 4. And since that's something very recent, I'd like to give you that example now. And I would like to use that to motivate some of the activities we are developing out of that for gravity. Now let me get you an exact 4-dimensional quantum field theory, which has an exact interacting UV fixed point. It's going to be a theory which is involving, first of all, so the way of the construction was as follows. I want to talk about gluons. So I assume that I say, have SUNC gluons in my theory hanging about. So there will be some type of Young-Mills coupling, alpha, of this form here, without addressing because the coupling is dimensionless. Okay? So this coupling is going to obey some RG beta function. Since I'm strictly in 4 dimensions, there's evidently no linear term up here. But it then continues with minus b alpha squared. And then, of course, in order to see potentially an interacting fixed point in this coupling, we at least would have to go to the 2-loop level. So at 2-loop level, there will be some term c alpha cubed. Now, of course, if there is a fixed point, well, an interacting fixed point, we can immediately read it off of this equation. But there is, okay. Now, how can we achieve this? Remember, in our previous construction, we had to make sure that A is an arbitrarily small parameter to have perturbative control.
I don't understand. You're looking for an infrared fixed point?
No, an ultraviolet fixed point.
But if you start
The signs are confusing.
you're not going to get it.
Yeah.
I come to that.
Right?
Yeah, come to that. Okay? So this would be the construction idea. Okay? So what I need to have perturbative control over this line of reasoning is the following. I take NC SUNC with NF fermions, and I take a Veneziano limit in such a way that I'm sending NC to infinity, I'm sending NF to infinity, but I make sure that a quantity which I call epsilon, which is NF over NC minus 11 over 2, stays finite. Now, why would I be doing this? I'm doing this because then the one-loop coefficient B is nothing else but minus 4/3 times epsilon. So, okay, so that's the trick or the technical tool I'm going to use to make the parameter, the one-loop coefficient of the Young-Mills beta function, as small as I want it to be. And this is going to be my perturbative control parameter for the entire consideration. Now, as David already pointed out, if I only were to be playing this game, the name of the game being coupling gluons to fermions, but nothing else, then Caswell already told us back in 1974 that C comes out positive. You can just compute it. C comes out positive. So, what does it mean? If the theory is asymptotically free, asymptotic freedom means B positive, then this fixed point is physical. Okay. However, it is an infrared fixed point. So if one were to be plotting the beta function for this coupling, it starts out negative because of this term, and then the positive correction of C gives you the famous Caswell-Banks-Sachs fixed point, which is an infrared fixed point. So, punchline, gluons and fermions alone cannot give you an interacting UV fixed point in perturbation theory. Full stop. End of story. So in order to change the storyline here, you would have to allow for scalars. If you allow for scalar degrees of freedom as well, fundamental scalars, these scalars have all the right to couple via Yukawa couplings with the fermions. The Yukawa couplings are going to contribute to this beta function, and the leading order where they contribute, it's 2-loop order, and a new coupling, the Yukawa coupling, is going to appear. We know exactly how the coefficient looks like. We can compute. We know the number D comes out positive. Okay. So the decisive point here is that because of the Yukawa coupling, there's an additional relevant, important minus sign coupling up due to the fermion loop. And this is therefore a term which can counteract this contribution coming into play from the gluons. So let's see how this is changing the result. Okay, so if I now say, okay, I want to explore whether this theory can become asymptotically safe. So I have to push it out of its comfort zone where asymptotic freedom would persist. So what I want to do is I want to be B being negative. B is negative, this term is positive. So my beta function for the gluons would start out like this. It starts looking QED-like and not QCD-like. Okay? And my question is there a way for this to come back and develop now an interacting UV fixed point? And the answer is yes, and I will show you how it works. The reason for this is indeed the fact that we allow for fundamental scalars to hang about. Good. So I said to make this potentially happening, we have to allow for Yukawa couplings. Now, if we have these Yukawa couplings, we also have to retain the running of the Yukawas. Now, how does the running of the Yukawas look like? We know that it's a positive number. Let me call it E, alpha y squared, minus another positive number. Let me call it F, alpha gauge, alpha y. That's the leading order beta function for the Yukawas. Okay? So, now it's a totally trivial task to ask yourself, is this coupled system of RG equations developing an interacting UV fixed point? Yes or no? And the answer is it does, and there is a necessary condition for it. And the necessary condition for it is as follows. Provided that dF minus CE comes out positive. So remember dF minus CE, so it's a relation between the two loop coefficients in the Young-Mills side and the one loop coefficients on the Yukawa side. Yes. If this cross correlation, I mean, it looks like a determinant of some sort, comes out positive, then...
What do you mean by Yukawas? Are you putting it in fermions?
I have fermions, or else I cannot push the Young-Mills theory out of its... I need to have fermions anyway. Okay. So there will be fermions. Okay. Otherwise I cannot... Young-Mills otherwise always is asymptotically free. So I need the fermions to...
Well, your alphas are what?
So alpha, yes. Okay, so let me be...
Anyway, so they can...
So alpha...
also destroy asymptotic freedom just as well as the fermions.
So alpha is this.
And you also need another fourth scalar interaction.
Yes, I have it.
Where is that?
It is not contributing at this loop level.
Well, it depends what it does.
It's not contributing.
For an ultra fixed point, and lambda is getting large, obviously it will contribute to it.
Yes, yes, of course. Yes. Okay, this is why this is... So, yes, we've studied that. So, first things first, this is a necessary condition. And then comes a sufficient condition. And the sufficient condition is exactly as you said. Okay. There must also be a UV fixed point in the scalar sector, part one. And part two, the fixed point must be such that the potential, in fact, is a stable potential rather than an unstable one.
Or at least three couplings that you have to control.
Correct, yes.
So
yes.
It can't be conditioned just on this.
As I was saying, there is if this condition is not fulfilled, I don't even have to look into the scalar sector. So it's a necessary but not a sufficient condition. Okay? So the sufficient condition then is if this fixed point is there, then we also have to make sure that it's countered by a fixed point in the scalar sector when the scalars speak with the fermions and indirectly with the gluons. Okay.
You still want the couplings to be small?
Yes.
Absolutely.
Okay.
So you have to have, again, be small thanks to...
Yes. So the point being this. If this necessary condition is fulfilled, then alpha gauge develops a fixed point, which is of order, let me call it epsilon, and positive, so physical. Alpha y is going to develop a fixed point, which is of order epsilon. Okay. Now this holds from this point of view of the necessary condition in all generality for generic gauge Yukawa theories. Okay. Now if we want to answer the question regarding the scalars, this can no longer be done in all generality. So you have to put your feet down, write down an explicit model, and work that one through. Okay? Let me give you an example, a completely worked out example. So, consider SU and C Young Mills. Okay. We consider NF fermions. So these fermions Q, right, carry some gauge charge. They have Yukawa interactions with uncharged scalars in the bifundamental of SUN. So the Yukawa interaction is something like Y trace Q bar left H Q right plus Hermitian conjugate. And in this theory, the scalar sector, as I said, we have now scalars in the bifundamental, so it's a matrix, uncharged. So we have this kinetic term, and there will be, in this theory, there will be two quartics we have to take care of. One which is H dagger H to the power squared. Okay, so the first quartic interaction, and there is a second one, which is H dagger H, so the trace squared. Okay, so quantum field theory with 4 classically marginal couplings, okay, with totally well-defined interactions. So for this theory, you can now sit down and work out the beta function in perturbation theory. So we did so up to 3-loop order, but as I said, the important thing is really happening at the 1-loop and 2-loop level where the fixed point is generated. So if you now work these things through, you will see that the theory has a UV fixed point, and it has the following features. We can, so now, of course, expanding them as a power series in epsilons means we have a specific model, so we can compute the specific. Pardon me?
What is it? Epsilon is defined as before? Or what?
I'm sorry, I didn't understand.
You're adjusting the flavor content to make something
Yes.
small like before?
Now, the flavor content is, we have NF flavors of fermions and a matrix scalar field, so NF times NF matrix of scalars.
That's a lot of scalars.
NF is
yes, it's a lot of scalars.
But they contribute the beta function.
Yes, of course.
Enormously.
They contribute to the beta
You
function.
cannot take the limit where you keep NF over NC.
Of course.
No, they will.
Yes.
They will make B enormous.
No, that's it. We get finite, well-defined to leading order. You make a
What are
Venetian.
you adjusting the B order epsilon? The beta function, I think B.
I'm adjusting only the 1-loop coefficient B.
Okay.
Then I'm
Could you write
finding.
down- Could you write down how that depends on NF? Because we don't know.
Here it is.
No, that's
But
just
why
for
the
fermions.
why the
That's for
scalars don't
fermions.
contribute?
The same.
Sorry.
For the total number of
Of bosons is NF times NC, so they would dominate.
They are
the
not
beta
charged.
function. They are not charged.
That's what I'm saying.
Ah.
Yes, we have the flat derivatives here. So they are not charged. Okay. Okay. So I'm using the fermions.
You say bifundamental in flavor, or in
Yes.
some kind of flavors.
Yeah. Yes.
Okay.
They are uncharged under the SUN. Okay. But I need them to construct, some easy Yukawa interaction, which is having this form. Okay. That's why I need them in the bifundamental in this model. Well.
Of some flavors.
Yes. Yes. Yeah. Good. Anyway, that's the model. So now you can sit down and just do the algebra because all these things are known, and you find, that you get some power series in epsilon for expanding all these couplings, alpha G, alpha Y, 2 plus whatever higher order. We've computed them up to order epsilon squared. Okay. So now maybe the interesting one is the one related to the quartic. Okay, and so this result here is a non-trivial result, but once more, So the non-trivial result is that this coupling comes out positive, and the way to understand it is that because the beta function for the quartic is very similar to this one. It has the quartic squared minus a contribution which mixes with the Yukawa. The minus sign is again relative, coming from the fermion loop. This is why two positive quantities can cancel, and that's the reason for why this fixed point can come out positive. So we have a setting in which suddenly a scalar field can exist fundamentally at highest energies, okay, with an interacting UV fixed point, which is physically meaningful. So roughly it comes out as 0.2 epsilon. Good. Now, the double trace coupling, interestingly, comes out negative. But the important point here for the stability of the theory is that as long as the sum of the two quartics, so alpha u plus alpha v, is positive, which it is, the theory is physically stable. It has a potential with a minimum in the symmetric phase of the theory.
Sorry, is that, do you have to normalize everything by the number of fibers?
Yes, they are normalized.
But not in your...
Okay, let me give you the normalization. So alpha u is essentially u times nf, because that's the single trace, and alpha v, which is the double trace, it's v times nf squared.
So how many relevant eigenvalues?
Yes. So now that we have the fixed point, of course, the next...
NF is good, and which is the negative one?
This one, the double trace.
But since NF is going to infinity,
No,
isn't that unstable?
No, it's not. It's stable because of the double trace here. You see, with every trace we get an NF, and then you work your numbers through. So then that's the normal. In this normalization, these quantities are order 1, and all NF dependence is out.
Okay. Can I just comment on, and this is of course not very similar to supersymmetric PCD where we know tons of.
I come to that. There's no supersymmetry.
I understand.
There's zero supersymmetry in this field.
Okay?
I'm talking about an exact example in 4-dimensional quantum field theory which has a UV fixed point. So it's strictly dynamical phenomenon, and it so turns out there is no.
I mean, you can.
What he's saying is there is a UV fixed point which is 0.
Yes, the totally flat 0, of course. Yes.
Plus a UV fixed point.
Yes, it is. Of course, it's a totally flat beta function. Of course, we know that.
And this is a small deformation, but it's not.
I mean, there are times you can have n equals 4, n equals 2, n equals 2, n c, n equals 1. You have the control window.
Yeah, but that it's completely different to have a fixed point.
Right.
This has a fixed point. Those have.
No, but
modular
I have
fixed
other
points.
fixed points too.
Those also have isolated fixed points in theory. I mean, sometimes you have fixed lines, but most of them have fixed points.
Good. So let me take some bits away. So the question came, and that would have been my
But
next.
anyway, since you're going to get the gravity. I mean,
Yes, okay, yes. I apologize for my slowness here. Okay, so we have the fixed point. This fixed point has 4 couplings. 1 of them is relevant. 3 are irrelevant. Okay? This is how it comes out. Yeah, so if you want to kind of make a plot, yes, it's like classically you have 4 marginal couplings. Okay, if these are the eigenvalues theta. Now you switch on quantum fluctuations. Let's parameterize them in terms of epsilon. So you find 3 of them are of order epsilon. Okay, 1 is of order epsilon squared. That's the one which is the relevant operator. So one linear combination of these 4 invariants is a relevant operator. And that relevant operator is dominated by field strength squared, so by the gluons.
So are these all the couplings that are allowed by effective field theory, or is this a fine-tuned fixed point? I mean,
no, these are all of them which are allowed in a massless quantum field theory. So you could, of course, also, and you could, and you should, maybe add mass terms.
Right.
Then those will also get fixed points.
Oh,
But end of story. Okay.
So they will also get. Is that known? What happens if you add mass terms to the scalars, for example?
They will get fixed points. We have not put it out yet, but I mean, this is what comes out of the equations. Yes. They will get they will settle on a fixed point as you would expect them to do.
But there'll be additional mass terms there.
Yes.
Additional relevant operators associated
Of
with
course,
mass terms.
yes. Okay. That's okay. Now, but the whole point here would be that, of course, if you now think about higher dimensional operators, okay, they will stay irrelevant simply because this is a UV fixed point which is perturbatively close to a free field theory fixed point. And so all corrections to anomalous dimensions in this case are controlled by a small parameter, which in this case is epsilon. Okay. Good. So let me now perhaps no longer bore you with non-gravitational business, and let's now come back to gravity. Okay. Now in gravity, as we were saying, the only result in perturbation theory, is in 2 plus epsilon dimensions. So the question is, can we uplift this type of result to 4 dimensions? Now necessarily, you would be fishing in the non-perturbative territory of your theory. And this is something which makes life horribly complicated in some sense. And just to highlight that a little bit, let me make a small comparison between theories which have asymptotic freedom and theories which may have an interacting fixed point. So in asymptotic freedom, of course, by its very construction, we know that in the UV, the theory will have a free, non-interacting fixed point. So consequently, we know that anomalous dimensions of operators all are approaching 0 if we go to the UV. So as a consequence of this, we know before even doing an explicit computation, we know that canonical power counting is applicable. So therefore, we know what is the set of relevant, marginal, and irrelevant operators in the UV as a consequence of asymptotic freedom. So in particular, we know that operators such as field strength to some crazy power, 256 for example, are going to be totally irrelevant operators in the UV. Okay? Now that's something which is heavily exploited by our colleagues who are doing lattice simulations in 4D to study strongly coupled QCD at low energies, because they know they don't have to take care of these animals. They can write down a finite set of operators in the UV and then reliably simulate that theory to get interesting non-perturbative results about low energy QCD. Good. Now, if a theory is becoming asymptotically safe, what's different? Now, by assumption, yes, it means something remains interacting of some sort in the UV. So G star is non-zero.
Sorry, are you assuming that there's a CFT in the UV or not?
I would be very surprised if you have an interacting UV fixed point which is not having a conformal symmetry. So you might expect that some conformal.
I think we know plenty of examples not of that sort, where, but of course, the one worry is that locality might break down. For example, in integrable 1 plus 1 dimensional examples where you know the exact S matrix, manual touch theories, you start with a bad S matrix. It is known that there's no CFT in the UV. It may or may not be a low quantum field theory, depending on details. But it's not necessarily a CFT in the UV.
We can figure that out once we have it. So right now we want to look for something.
And when you say CFT, what about the leading running of the beta function, the fact that there's a Planck scale there?
Yeah.
That will remain in the CFT?
No, it'll float a strong coupling, and then there'll be a 0.
Exactly.
So even
the whole point would be the running of couplings comes to an end because there is a fixed point.
Yeah.
Okay. So the way, kind of, say, pictorially speaking, in some naive way, think of a 4-dimensional, in 4 dimensions, let's define some dimensionless coupling. Okay? So this thing in perturbation theory, way below the Planck scale, this would grow with something like this. Okay? If we plug it, say, log mu over, say, log g, yes, then this line would have the slope 2. Okay. Now, the problem, of course, with classical gravity is if you continue, let it grow, then this is what is causing trouble for the UV definition of the theory. But if then, close to the dynamical Planck scale, this guy is dynamically crossing over and settling to a fixed point, okay, of course, the growth rate stops. Okay, and effectively what happens is that in the deep UV regime, when mu is taking very large values, okay, G Newton, so the running coupling constant, which technically would appear in your effective theory, or Lagrangian, would scale with an inverse power of energy. Okay? So this is, in a sense, that the dynamical picture underneath on how an interacting UV fixed point in gravity actually can cure the divergences which you get from a gravitational theory, where classically G Newton would stay a constant, but quantum mechanically, due to the fluctuations of this field, actually these non-perturbative fluctuations result into a reduction of this interaction. Okay? Now you would say string theory has a different mechanism. String theory would say, okay, up to some energy scale it's low, it's just simply gravity, but then we realize that the world is higher dimensional, of course, and then the string scale is generating a kind of leveling behavior for if we would want to look at this running. I mean, it would also settle off, but then this scale is set by the string scale. Okay, it's just a dynamically different mechanism to tame the fluctuations of gravity.
But I mean, are you saying it's actually a CFT in the sense that there's a local stress tensor that acts within the physical Hilbert space? I mean, that's a little confusing.
I don't know that.
There's gravity.
I don't know that.
Variance, right?
I'm not saying any of these things.
I haven't heard any claims yet. He's just talking about problems. Why don't we wait to see what he claims?
So for now, yes. Yeah. Okay, so I haven't said that because I don't know. I don't know whether this would be the case. The only thing I did say is that if such a theory has an interacting UV fixed point, simply because it's a fixed point, I would expect that some version of conformal symmetry is explicitly realized there, because this is what we typically find. But there may,
It might be a gauge symmetry.
Exactly. Who knows what that is? Okay, so if people have some input coming from the other end, maybe this may help in making progress in these cases. But
There's also a question of what such a picture would mean in the following sense. In, say, asymptotic freedom, we know how to probe the regime where the coupling is going to a small value by doing, say, scattering at high momentum transfer.
Yes.
And if you ask the same question in gravity, high energy scattering with high momentum transfer, there are some arguments that seem to strongly indicate that the picture is very different from probing the Newton's constant at a large momentum transfer because of a phenomenon known as momentum fractionation.
I comment on that. If I make it to that point, I will comment to this roughly here.
Yeah, it does.
Okay,
even
because
before then it becomes an issue, even in the iconal regime.
I know. Well, I wasn't about. I mean, we did study the iconal regime, the iconal scattering in this setup, but that will be a different talk, I'm afraid. But I mean, I'm happy to share our results.
Again, I'm just asking for moving forward.
Yeah.
What would one mean by this? By a theory which had Newton's constant somehow. How can Newton's constant at large momentum transfer, ultra Planckian momentum transfer? Where does that enter into the physics of a theory?
Yes, very interesting question, and I think I will try to let you know some of those things which people have discovered in that context. But
I mean, there are other, as you say, as in this case, there are other relevant or marginal operators in general that you're going to have to consider.
Yes.
Like R squared.
Yes. I come to that.
You are about to talk about those.
Yes. So I wanted to make.
That's going to be the next
No,
line.
that's
right?
the real problem. Yeah. So
No, I don't think that's true, though. The ultra Planckian, that's the discussion we had a few weeks ago. right? Those only dominate short distance physics. The problem is at very high energies, we're talking about long
different
distance
ways of
physics.
doing high energy.
Yeah, that's maybe. Well, let's.
Okay, anyway,
Why
let's
don't you let
before you have
it
a-
Okay, so now
the crucial point. Eta
yes.
now
So
is not zero.
we are in the setting where we would like to talk asymptotic safety. So eta typically anomalous dimensions of operators is non-zero. So most importantly, we do not know a priori what is going to be the set of, let me call it, scaling exponents, these guys. Okay?
You're assuming local operators do exist, by causality and all that.
I have a notion of writing, so I am imagining probably of writing down an action which has diffeomorphism invariant operators with couplings in front of them. Okay? Yes, and so maybe local, maybe it's not necessarily local, but I'm having this view, and I'm having the view that if this thing is developing an interacting fixed point, I can measure universal quantities which teach me something about that theory. These universal quantities are these universal scaling exponents. We know them in asymptotically free theories. We don't know them a priori in an asymptotically safe theory. So we don't have guidance. Okay? So in particular, if you think of the following question, which Emma Nicolai asked me a few years back, say, well, Daniel, you do all these computations here, but can you tell me whether, say, some curvature invariant to the power 256 is going to be a relevant, marginal, or irrelevant operator at your UV fixed point? Okay, what is the answer? Now, the whole point with this question is, he has a point. If you don't know a priori anything about the UV behavior of your theory, how can you, with a finite set of operators, look for a fixed point? How would you know that this is the final and a reliable answer? How would you know that if not, one day somebody comes along and can take, many more operators into account, and when suddenly something crazy happens and these guys become relevant rather than remaining irrelevant? Okay? So, which would mean that some of operators maybe get extraordinarily large anomalous dimensions. Okay? It's a question of principle. Yes? And it's not a question which can be answered by just...
The question is even worse. You have already right in the vicinity of the infrared fixed point, which is otherwise known as Einstein gravity.
Yes.
You have an operator of dimension 0.
Yes.
Of dimension 4.
Also.
Okay, so it's not as if it's going to somehow become relevant or not relevant.
No, there are already relevant ones.
Whatever you know, it looks awfully relevant.
Yes.
In ultraviolet.
Yes.
And it is orthic in momentum.
Yes.
And you have a big problem.
Yes. I totally have a big problem, but I even have a bigger problem. I even have a bigger problem. The bigger problem, I think, is...
And the combination of those R-squared operators remains dimension 4 to all orders of integration. So it's unlikely that there are going to be others which are not related to the Euler character of the are going to suddenly get very far away from 4.
Yes.
But again, I don't understand. In the infrared, you say, well, I'm happy because all the anomalous dimensions are small. But if you look at the ultraviolet,
yes.
What does it mean irrelevant? Irrelevant in the ultraviolet. It's not irrelevant in the usual sense of infrared irrelevant.
Yes.
Yeah.
If you assume that the CFT in the UV, then it's meaningful.
Then it's meaningful, yeah.
But otherwise, it's not clear what
Well,
it means.
it's not clear to me what it means. Do you need an anomalous dimension of 256?
Just to be
To make, you would need such a large anomalous dimension
Do you
to
need-
make an... No, I don't need it. But you need it to make an irrelevant operator relevant. And the question here is, can I convince myself that...
Get rid in the ultraviolet of such an operator?
So he wants to get rid of ACOs or ghosts.
But this is, just to be clear, this is a practical problem, right? If we tried to write
think
down
it's a
QCD using the pion fields, of course, that would be a very difficult process. But that's not that doesn't mean that there's not going to be some sensible UV theory. There might
Exactly.
be.
Yes.
Yeah. It's just writing it down in terms of
Yeah.
pions would be stupid.
Yes.
Right.
Okay, in the spirit of QCD, yes.
It doesn't mean, but it's, given what you know, the little you do know, it looks dangerous.
You say it looks worse than the pions.
It looks worse than the pions.
It's more like boring out rather than nursing one.
I mean, you're asking a different question, which is the question, can a nonlinear sigma model, or this pion theory, develop an interacting UV fixed point? Okay?
Yeah, apparently the answer is yes.
Yes, so it's a fair question. It's not necessarily guaranteed that this is the UV physics of QCD, and in fact we know it isn't. Okay, but from a field theory point of view, that is the type of question you can ask. So, yeah. And there's some similarity, of course, between that model and how gravity moves. Yes, so they have similar problems. There's another question.
I'm a little confused about how one would define these terms in this safe point. Partly because of something that was asked earlier. I thought we know that there are no diffeomorphism invariant local operators. I mean, you're almost able to show that. So what does it mean to define all of these?
Yes. So imagine you would want. So what I'm having in mind is perhaps following. Imagine you write down an action.
Let me rephrase. So how could you probe the relevance or irrelevance as a statement of properties of the S matrix?
Okay, good. Look, I'm not talking about the S matrix for now. Okay, we can open all sorts of cans of worms now. But okay, S matrix is a different business here. Okay, I'm not really, talking about it right now, but I'm happy to speak about scattering.
Well, there are a lot of formal things we don't understand about the structure of quantum gravity, but a test of the structure is to go after the S matrix. In fact, that's how Weinberg originally proposed thinking about asymptotic.
That's perhaps one way one could follow. I'm now following a specific way, and I'm trying to make a point here. Yes, and so let me try to make that point for once again, because I still think. Say, since an asymptotic, if we have an asymptotically free theory, we have non-trivial a priori information about that theory. And this information is extraordinarily valuable because we know what is the set of relevant and marginal operators in that given theory. This then means that we can, in actual computations, convince ourselves that indeed this picture is dynamically stable, whatnot, we can simulate such theories. Okay? Whenever we speak about a theory which potentially has an interacting UV fixed point, we would not know those things a priori. So we would have to put in some effort and some, say, strategy in order to convince ourselves that perhaps such a fixed point really exists in a physical theory, or possibly not. Okay? I gave you an example of a four-dimensional theory, okay, where we have an interacting fixed point. Now, the difference between this and strong, say, 4D gravity is that in that case we have a small control parameter. Because of this small control parameter, we are arbitrarily close to something which in fact is asymptotically free, in the sense that we still know the operator ordering in this theory. Anomalous dimensions are perturbatively small, so canonical power counting is applicable.
Are the results in 3 plus or minus epsilon dimensions? Is there an expansion around 3?
Gravity?
In gravity. Since 3 is special, in some sense trivial, is there?
Yes. I'm not aware of those.
Dimension for a couple.
Yes.
It's not the usual one, but is there?
No. Maybe. Wait. I'm not aware of it. Good.
So sorry. Okay. Can I just say? I mean, the assumption that there's a low quantum field theory in the UV is an extremely strong assumption that we usually don't believe is.
Well, I mean, let's put it this way. Nature has shown everything which nature has shown us to work and which we can measure in an experiment are local quantum field theories. So I don't think it's.
Let me give you another example.
It's a little tricky here because I mean this is a little different because you don't want to introduce. Are you going to introduce other fields? So when you say
I don't have the intention.
What's the context? You have a theory of space-time.
Yes.
Diffeomorphism invariance. You already have a field.
Yes.
That you must.
So I'm trying to imagine that the dynamical carrier of the gravitational force continues to be the metric. I wouldn't object.
You have a metric.
Yes.
So you have a dynamical field.
Yes, totally. Yeah.
And any other fields?
Well, if I let gravity speak with matter fields, which sooner or later they ought to be doing, then I will couple them to conventional matter. Yes, but nothing other than that.
You can ignore the matter.
Yeah.
So we just have the gravitational field. So you're saying you have a coupling. If you define Newton's constant to be a critical value, is that what you're imagining?
I'm imagining.
And then you don't have perturbative control over the fields, that you'll have some action which is a functional of it.
I'm imagining an action which is a functional of yes, derivatives, possibly coupled to matter fields. Okay.
Well, if they do, it'd be good to get to that.
So
maybe you should, if he has a proposal for the fix for this, maybe you could,
So,
well, that theory has no scale except the coupling itself.
Well, it has a cosmological constant. Yes, it has Newton coupling. It may have higher dimensional operators which introduce scales by themselves. Okay, who knows what the action will look like? Okay, and also the way I would be looking at it is actually the other way around, kind of, because I want to figure out whether some dynamical theory of the metric field would be willing to develop an interacting UV fixed point. So I wouldn't want to have too strong a prejudice on what the action actually is. I would like to figure out what that action must be so that that theory is having such a fixed point. Okay? Now, but if I phrase the problem this way, of course.
You know what that action must be in the infrared. Right?
Of course, I know more or less what it is. I mean, observationally, of course, R-squared couplings are very poorly constrained, so they might be hanging about. Maybe other terms are hanging about as well, but of course, GR is the predominant. I mean, Einstein-Hilbert is the low energy limit of such a theory, of course.
So I was kind of hoping to find out how this connects to black hole thermodynamics.
Yes. Okay.
I wonder if we need to invoke the 10 minutes of uninterrupted time.
Sounds like a great idea.
Okay. Well, look. I tried to make a point. You may or may not buy it, but you see, if we have a theory which is, if we are looking for a theory which potentially can become asymptotically safe, then finding or convincing yourself that you have found one such example, yes, is really a bit more challenging due to the lack of a priori information. If we were to be known, if some of you tells me, well, Daniel, it must be this and that set of invariants, well, then in a way we would be done because we know this set of invariants. Then you choose your favorite set of tools, RG, lattice simulation, maybe holography, who knows. You take that theory, you identify the fixed point in that operators, you compute the universal scaling behavior, and then we, have a handle on tackling this theory. But if you don't know that beforehand, it's trickier. So what we tried to do to circumnavigate this problem is to compensate the absence of a priori information by a hypothesis. Okay? So one way of looking at it is to say, okay, I throw a hypothesis into the game, but then I can test or check the hypothesis in a systematic order-by-order computation. So the hypothesis we've been putting forward here is the following. We're saying, okay, we're assuming that the canonical mass dimension of invariant is going to continue, to control the relevancy of invariance at an interacting fixed point. Okay? Now, where is this hypothesis coming from? So in essence, it's saying the canonical mass dimension continues to be a good guiding principle. Okay? Now, why it's a useful hypothesis? First of all, essentially all interacting fixed points we know have that feature. Okay? Secondly, why it's useful? It's useful because it's falsifiable. How would it be falsifiable? Well, you could say, let me take some action with invariants. Let me classify it according to their canonical mass dimension. Okay. let me stop it at some maximum order. I use then this action with my favorite technical tool to figure out, is the theory having a fixed point? If yes, what are its scaling exponents? Okay. Then I throw an additional invariant into the game, an invariant which is having a higher mass dimension than all those which are presently in the game. And I redo the entire analysis. Analyze the equations, look for fixed points, compute the scaling exponents. And then you iterate until you get tired, I guess. Okay. But then you see from order to order, you can actually plot fixed point coordinates, universal exponents. You can see from order to order whether at the next order, the scaling exponent, which appears in your set of scaling exponents, whether it is indeed a scaling exponent which is less relevant than all those you found previously. Okay? And then you throw another operator into the game and you just go on doing it. Okay? So this would be a mechanism by which, in a sense, guided by some principle, which, however, you could now falsify, okay, whether your fixed point in some approximated study of gravity is having this feature. Now, if it is having that feature, of course, this would be very nice, because then you would say, okay, yes, maybe it's not so completely wrong to simply approximate our actions with some finite set of invariants, okay? And then this would be a sign for higher order invariants to indeed remain irrelevant. On the other hand, if you would observe that you don't find a fixed point which offers stability on that level, then the answer would certainly be to the negative. At least you would have shown that your hypothesis cannot be satisfied. Okay? This, however, then may not necessarily mean that there is not the fixed point, but however, in that case, I wouldn't know how you can systematically prove the existence of such a thing. So that's the game we decided to put forward in order to address gravity. Now let me give you one example. Okay, so imagine you have an effective action for your metric degree, for your metric degrees of freedom, just metric fields. We also extended it to coupling it to matter fields, but that's a different study. Okay. Now we make one model assumption, which certainly or most likely is not true in real gravity. Okay, which is that for this study we assume that the action is a function only of the Ricci curvature. Now that's only due to the technicalities in actually getting all the RG equations for the couplings, where we are limited by technical issues for now. But what we can do is we can study theories where we have invariants of the following form, say determinant of G mu nu, whatever, some power of the Ricci scala. We can extend that, and we did, to also study more complicated curvature invariants like contractions of the Ricci tensor and such like. Qualitatively, we'll get the same results. So imagine you have a theory like this. Imagine you want to study the RG running of couplings. So let me call the RG scale mu. Then these dimensionless couplings have RG scale mu. Dn here is the canonical mass dimension of the coupling. Let me call it consistently mu. Okay. So this will be our dimensionless running coupling constants. For these guys, we need RG equations, and we are going to use a technique very similar to Joe's RG equation, except that we use a Legendre transformed version thereof. Okay, so
sorry, maybe I missed. The R2 again, that's literally Ricci scalar.
In this example is Ricci scala. As I said, you can extend it to study other examples. You can extend it to study R-squared gravity. These are the cases we can do, and we can do all sorts of functions of certain scalar contractions, just as functions of R mu nu, and contractions of Riemann squared, and these type of.
Don't you need to actually start with the Riemann, because otherwise this time at least the first one can be removed by pure definition. It's not physical.
No, it cannot.
First order you can.
Not in the full quantum theory, no. Okay. And
these
so
these terms which have the largest number of the things that would really bother you you think would be the things with large, more coherent derivatives.
Yes.
Those are likely to develop a causal over.
Yes, exactly. Yes.
And you're not including them.
People have not yet looked into that very systematically.
But you say you have looked at the Riemann cube terms, Riemann fourth terms, or something that aren't just off.
Yeah. Yeah. So we looked into this. I can show you some results of that. We looked into actions which involve powers of this, maybe dressed with Ricci scalars, whatnot. I mean, okay, good. There are certain games which technically we can play.
But I just wanted to check that the non-trivial Riemann contractions that don't reduce the vinyl tensor contractions are included in the list of things you've been talking about.
Yes.
Okay.
Yes. So, the type of result you find is that A. So, what's the name of the game here? The name of the game would be you fix n, namely the maximum number of invariants which you retain. Increasing n from n to n plus 1 then means you take the next higher curvature invariant into consideration. It will shake up the system. So it's a reasonably complex set of equations. So you would have to reevaluate those. But what you find is that from order to order, indeed, these set of RG equations for these couplings develop a very stable ultraviolet fixed point from order to order. So I have plots, I mean, good, okay. Not so good.
That ultraviolet fixed point is very small. Lambdas are small.
So you get, lambda are numbers, okay? So you get certain coordinates for these. So lambda 0 would be related, of course, to the cosmological constant. Lambda 1 is effectively related to Newton's coupling and so on and so forth. So lambda 2 is related to the R squared coupling and so on. Okay? So these numbers come out order 0.1 to 1 in this way of computing things. So remember, these are dimensionless couplings, okay, all rescaled by the proper RG scale, okay? So
that's
this is
mu to the dn. I mean, it's a negative power of mu.
Yes.
Typically.
So let me see. Yes, so dn, the canonical mass dimension of these guys is 2 n minus 2. Just, okay.
So, sir,
there should be a minus sign.
R to the n terms, I'm not understanding the physical meaning of these coefficients. These are not invariant under pure definition.
Pardon me?
These are not invariant under pure definition. What's the meaning of this?
I don't care. I don't care because it's a coordinate system. And of course we know coordinate systems for fixed points are not universal. So I couldn't care less. Okay? What I would care about is the stability of universal scaling exponents, because this would technically be quantities you can measure in an experiment. Okay? So for now I choose some coordinate system, and I want to figure out whether I have a stable fixed point in that coordinate system. And I don't care about universality here because there is no such thing. Okay? Now the answer, however, is that...
computation is done.
Oh, sorry,
These
yes.
things have large leading order beta functions which come from the classical dimension.
Of course.
How's the computation done to find this fixed point in perturbation theory?
No. The computation... Okay, good, look. I will try not to bore you too much with technicalities here, but I mean, it's not... you cannot do it in perturbation theory, at least not in an obvious way. So the way we do it, we use Wilsonian type renormalization group. Okay, so it's based on the idea that we have some path integral representation for our theory, okay, from which we integrate out momentum degrees of freedom. Okay? If we have that, if we have that, then we can formulate a quantity which I call maybe a Wilsonian effective action, which I give an index mu. Mu is a momentum scale, and mu is the momentum scale up to which, or down to which momentum degrees of freedom have been integrated out. Okay, so that's the object I'm interested in, because this object, which I'm now writing down as an action like this, and where I view the energy dependence of couplings as being related to the running of exactly those couplings which parameterize that action. So the running of this coupling is now teaching me on how integrating out further momentum shell.
How do you integrate out if you don't have perturbation theory?
No.
So
Yes.
how do you do it?
So the way I do it is I throw a momentum cutoff technically speaking, into the theory, and I ask my theory, how is it depending on this RG, on this Wilsonian RG scale mu? Okay, and for this, I can write down, or people have written down exact equations. Yes, just to which look like this, plus some Wilsonian momentum, plus R times, well, mu, dd mu, acting on the Wilsonian momentum. Okay? So we write our theory with a technical tool in the theory, which is cutting off momentum modes, so that we, in fact, can do the integrating out. So that's one possible way of simply doing it. Okay, this way of doing it gives you all the beta functions I've discussed in the Gauge-Yukawa theory. This way of doing your business, if you do it in conventional 4D QCD, shows you the transition from perturbation theory to, in fact, confinement in the infrared. So we know that the technique is powerful enough to indeed describe such non-trivial features of quantum field theory.
Normalization of equations, but solving them non-perturbatively is a different matter.
Yes. Yes.
And aside from the fact that it's not, coming back to the question here, it's not clear that this closes because R to the n is not the complete set of operators. So
yes.
You don't. Normally, that will not close unless there's some miracle happening.
Yeah, that's indeed true.
So how can you
yes.
the equations aren't even frameable in this framework?
Yes, they are, because the way you do it is you say, well, of course, first of all, there are many ways of solving these equations. One way of doing it is you say, good, this is my action, these are my operators. Now, I want to deduce the running of the couplings lambda n.
The derivative of that action, or integrating out fields, will introduce other operators.
No, I've integrated. This is the equation I want to solve. It's a non-perturbative type of. I mean, it's an identity of your path integral. Okay. So what I put in as part of my approximation. So now, what is the approximation? The approximation is.
Sorry, I disagree. If you start out with a complete path integral, or path integralism cutoff, when you change the cutoff,
yes.
In general, you will introduce new operators, even if you don't have them to start with.
That's correct. Yes.
And you only have there a sum of Ricci scalar to the nth power.
Yes.
So the derivative will, in general, involve other operators.
That's correct. And as part of the approximation we are using in order to evaluate the RG flow of these operators in this approximation, we neglect the operators, some of which are being generated along the flow.
Maybe approximation is not a good word for describing this. Maybe just simple, truncation, or toy model, something like that.
Yeah, but.
That's
totally fine by me. Okay. totally fine by me. Yes.
So can I ask though? But the leading term you get there is a -2 or a 2. I don't know, depending on the sign.
Yes.
If all of these couplings are small, how do you cancel that? How does that turn into 0? I thought you said here that all of these lambdas were small lambdas.
Well, they typically come out.
So I haven't understood how the leading terms, which are large numbers,
yes.
Aren't they cancelled by the explicit mu to the d, no? I thought.
So the explicit mu to the d is going away in principle.
No,
the mu you don't see it anymore.
The lambda depend on mu, right? You look at how the lambda.
Exactly. Yes.
And so maybe that. So I think it's the deviation from canonical dimension.
Oh, is that right? Is the deviation from the canonical dimension? That's what I was asking in the beginning. Is it
the couplings are dimensionless, so we scale out their canonical mass dimension. And then you get an autonomous set of equations for all the couplings lambda. So if we call, I mean, some of this is really terminology, namely the terminology on how you would want to, define your approximations. Yes. So if you want to call it a truncation, fine by me.
What is capital N in your definition?
So that dimensionless?
Capital N is the number.
I know, but what actually do you do? N equals 1?
We went to 35.
There is n minus 1.
No, but that dimensionless coupling, I thought, there's a Planck scale sitting there. As you rescale the Planck scale, you have a certain effective action. You need to scale that number. So how do you get to keep the low energy Newton's constant fixed? Presumably, you need to scale that number as you change the cutoff.
Which
So,
number?
I have a proposal.
You need to scale the dimensionless number that multiplies the cutoff.
So we have there's another.
No,
thing
but I mean that's.
Can we just assume? Can we grant him that the fixed point exists and then hear what he says about black
I want
holes?
to know what the fixed point is.
Yeah, I'm wondering.
Of course, yeah.
What is the fixed point?
How long will it
Can we
take you
just
to
fight
say
about
what
this
you
forever?
say about black holes?
Good.
That's a whole other talk, I think.
Yeah, I'm wondering if.
Yes. Well, as you.
Just give us the 30-second version.
I think it's better to finish this story because it's hopeless to do it.
But we're never going to settle this, right? I mean, the people have been fighting about this for 30 years, right?
Have they? Yes. Okay. So, David, n equals 35 is what we really computed.
So you tell me you set it, you find 0, 35 simultaneous algebraic equations.
Order by order, systematically. Yes, exactly. So the way you do. So it's like, look, there's one bit is conceptual. Okay, we want to implement an idea which we hope is going to help us in searching for interacting fixed points. Now then you try to implement that idea in a real computation. Now because it's non-perturbative, you have to throw some type of approximation, or let's call it truncation, into the game. Okay. So to illustrate it here, I wanted to give you an example where the theory is some high order, say, polynomial in the curvature invariant. Okay. So the way this particular type of computation then technically works is that what you do is you use this type of Wilsonian RG equation. Now, how do you use it? Technically, you need to evaluate an operator trace on the right-hand side. Okay, and this is what technically is the limitation, because we would have to do that non-perturbatively. So the way we technically do it is we use some heat kernel technology, which allows us to project this right-hand side on all sorts of curvature invariants. So then, by doing it, we can compute the right-hand side as function. So this will then become a function or another polynomial of Ricci scalars. And then we can compare the flow of these couplings on the left-hand side and read off their beta functions on the right-hand side.
What's gamma 2? You have gamma 2.
It's the full propagator of the theory. So it's the second functional derivative of your action with respect to all your fields. So it's a big matrix, good, which is then expressed in terms of certain differential operators acting on this background on which we evaluate the operator trace. Okay, so this is how, in this concrete example, you would be doing the computation.
When doing that, you generate other terms that you just throw away.
So, exactly. Okay, so because we said, well, we make a prejudice because of inability to compute the whole thing, okay, we throw those which are generated on the right-hand side, which haven't appeared on the left-hand side, we leave them out. Good. So, now what comes out? One plot. Okay. One plot. So what I show you is the set of scaling exponents, okay, as function of the approximation order. So on this axis, the little index n. So at approximation order capital N, I have capital N independent couplings, so I will find capital N eigenvalues theta n. The negative ones are going to be, in this normalization, the relevant operators, and the positive ones are related to irrelevant operators. So, a zero line somewhere here, the relevant ones will be downstairs, and the irrelevant will be upstairs. So what comes out? So what you see is that this theory, in essence, has three relevant couplings. Okay, and they appear indeed already as you might have expected, in the first three orders. So which in this way of parametrizing it, I think it's n equals 0, 1, 2. From the R cubed order on, we find that the scaling exponents are irrelevant. Okay? So if I now show you little dots here, what this means is it's in fact the overlay of 33 approximation orders. There's a very small error bar around these, certainly in the leading order exponents here. Okay, so we find very stable results, irrespective on how many invariants ultimately we are taking into consideration. First thing. Second thing is...
Something bothers me because let's see, in 4 dimensions, there are 2 relevant operators, right? And one relation, Weil tensor and Ricci scalar squared, and R mu nu squared is related to them algebraically.
Yes.
The topological. So if you have one, that upper one presumably is your R squared term, right?
So the R squared one is this one.
So how can you throw away R mu nu squared, which is equal, is equal to R squared up to a topological term?
Yes, I have done it in this computation.
Right. Okay. But you can shuffle them around.
Yes, I can shuffle them around, that's true. So, of course, it would be, we did the independent computation, which is the computation which retains cosmological constant, Ricci scalar, Ricci squared, and maybe Weil squared, which is one basis, of course. Okay. Just to be sure that this theory also has that fixed point, which has 3 relevant and 1 irrelevant direction in this case. Okay. But in this particular example, we were not able to also incorporate that second marginal, classically marginal operator. Okay, our focus here was more on the question, what is going to happen if we have further higher dimensional operators in the game, and whether we can see or detect a pattern according to which these, in fact, will stay irrelevant.
Yes, I'm confused. When you say R mu nu squared, you differentiate it from R mu nu from Weil squared.
Yes.
How do you do that?
Well, you can differentiate, say...
The difference between them is topological.
What you can do is you can differentiate between C squared and R squared, for example, by evaluating on suitable backgrounds which have sufficient structure. I mean, if you don't use just spheres...
But if they all have the same Euler character, then
Yes, if you evaluate them on certain Einstein spaces.
Is a function of those two, you say?
Guess today is a function of 3.
Three are constrained to be.
Yeah. 3. So he's talking about getting 2 out of 3, right?
Yes.
I think we have.
I'm just saying I can write one of them in terms of the other one.
Class does go in.
Take that into account. Yes, take that into account. Then it's
there are only 2 invariant, two independent ones.
2 fourth order.
Yeah.
So is it just as well to use then Weil squared? So then my question is, what happens in the ultraviolet near this fixed point to the graviton 2-point function?
Well, that's a different thing. We looked into the RG running of that 2-point function. So what we found is that we have meaningful RG trajectories which connect that UV fixed point with a reliable infrared regime. Okay, so we do see that there is no singularity along those trajectories, and it relates a little bit to work done a few years back. I forgot now who did that, where this question had been re-evaluated in perturbation theory. The idea being that you can use the Weil coupling as a perturbative small parameter. Okay. Yes, and if you do that, you actually also see the non-trivial fixed point for Newton's coupling coming out of that. So, the point I wanted to make here is this. Okay, you you find data kind of spread in some range, okay? But no matter what, all higher order invariants indeed lead to larger and larger eigenvalues, showing that these invariants essentially are increasingly irrelevant as compared to those which carry a low canonical mass dimension. Okay? So why do we think that this is something important? We think that this is structurally of some importance because it gives us some guidance as to how one should systematically phrase a search for a UV fixed point. It so would seem now that the canonical mass dimension is a meaningful guiding principle. Okay? So we would not, it seems as we have to worry less about Hermann-Nicolai type questions.
Well,
yes.
Let me ask, there's a question of signs as well.
Yes.
Stability,
Yes.
positivity, et cetera, et cetera.
Yes.
What are they?
Well, okay. So, first of all, I mean, of course, you know that this computation is done within Euclidean quantum field theory. Okay. So, in this case, we can compute these quantities. And what we do not see that the perturbative, say, ghost, is really hitting us here. If we compute these equations at the approximation level, which corresponds to fourth order gravity, okay, so Kelly's famous study some time back, okay, we do not see that the corresponding fixed point, which we have here, is showing exactly the same type of problems. So we are not. So
the quartic terms, you can choose the sign. Perturbatively just throw it out whatever you want.
Yeah.
But you're getting a fixed point. So what's the sign
of while?
Of while, for example.
Yes, they come out. So they come out positive.
They come out. So what? So the Euclidean action is positive.
Yes. Okay. Good.
But if Euclidean,
Well, we are way over time. We might, I guess, try to figure out how to organize some more time. I don't know, maybe next week. We've got various constraints.
Next week's the conference.
Next week is the conference.
Yeah,
How long are you
know.
here?
Yeah, but there are
Sorry,
some
I'm only
next
on
week.
next week.
Yeah, so we'd have to find a time when.
What's happening tomorrow?
But
Tomorrow afternoon, it's very hard to get rooms, and tomorrow morning we have a topic. So it turns out that I've been through this exercise. So anyway, but I think we should probably at least stop here.
Yes.
There can be more informal discussion, and we'll see if we can engineer something else more formal. So, thank you.